Good day, everyone. My name is Andrii Golubtsov. I'm a first-year student of Mechnikov National University and Matthew Bell National University. Today, I'm delighted to present to you a short journey from some interconnections between discrete mathematics, number theory, and analysis, three seemingly distinct areas that, when brought together, reveal deep connections and a shared mathematical beauty. So the motivation behind this research is, at the first glance, a derangement in combinatorics, the Euler-Stauchen function in number theory and asymptotic density results in analysis may seem unrelated. However, they share a unifying theme. Each captures the structure and likelihood of independence within a system. So let's start with derangements. A derangement is a permutation of a set where no elements appears on its original position. So for example, if we have three elements, 1, 2, 3, then the permutations are the sets where no element appears in its own position. So it's 2, 3, 1, and 3, 1, 2. And this formula represents this relation. So it's denoted by dn. And this expression may remind you of the Taylor series expansion of the exponential function, and rightly so. So in fact, as n converges to infinity, the ratio dn divided by n factorial is approximately e to the power of -1. This convergence is not only mathematically elegant, but also has probabilistic interpretations, such as in the hat check problem, where guests randomly retrieve hats, and we ask how likely no one gets their own. In this table is shown the results of this derangement and the convergence of this relation, and how quickly it becomes 1 divided by e. So now let's connect derangements with the broader class surjective mappings. If we have two sets A and B with n elements in both, every bijection is a permutation, and some of these permutations are derangements. But more generally, suppose the set A has n and B has m elements. Without loss of generality, let n be greater or equal to m. The number of surjective functions from A to B, that is, mappings, where every element in B has a pre-image in A, is given by that formula. And this is a beautiful use of inclusion, exclusion, and it shows how surjective functions count the certain kinds of partitions. Thus, derangements are a special case of surjections. They are bijections where no element maps to itself. We can think of them as fully displaced surjections. Next, let's look at how surjective mappings lead us to partition of sets. If we consider the number of ways to partition a set of n elements into exactly m non-empty unlabeled subsets, we arrive at the Stirling numbers of the second kind, denoted as S of n and m. There is a beautiful relationship in which the number of surjective functions from n element set to m element set divided by permutations of m elements is exactly equal to the S of n a m. which is shown in that formula. So here's the link. The surjective functions are closely tied to partitions, and derangements are again nested inside this broader structure. This hierarchy, from permutations to derangements to surjective maps to set partitions, is a cornerstone of enumerate combinatorics. And hence, let us now shift from combinatorics to a powerful tool in number theory, that is Euler's Tauschen function and its significance. This function counts how many positive integers less than n are co-prime to n. This function is not only arithmetically elegant, it is structurally profound. Consider a number of n with the prime factorization, and then Euler's product gives us that formula phi of n, that shows us the count of these non-coprime integers. In this table, we see how quickly and how broadly oscillates this function. That is because for prime numbers we have a unique behavior. That is because all the numbers that are less than prime number is co-prime to it. And this means that the phi of n not only reflects the number of co-prime integers, but it encodes the multiplicative structure of the set of all integers less than n that are co-prime to n under multiplication of modulo n. And but its importance goes far beyond pure number theory, because in modern cryptography, like in algorithms like RSA, Euler's function plays a critical role. The security of these systems relies on the difficulty of computing a phi of n without knowing the number, thus its prime factors, which is essential for secure encryptions. So the intuitive explanation is this table that shows us how quickly this number oscillates and how difficult it would be to know the factorization and the image of this function without knowing the number n. Interestingly, the Tauschen function also reveals beautiful analytical behavior. A remarkable result in number theory is that the average portion of integers less than n that are co-prime to it tends to a constant 6 divided by pi squared. So just as derangements, this gives us a limit approaching the limit approaching to 1 divided by e. The Tauschen function gives us a density approaching this number. That is two different problems, two different constants, but both linking combinatorics and analysis through limiting behavior. So in conclusion, derangements gives us insight into permutation structure and its convergence. Surjective mappings connect to partitions and Stirling numbers. Euler's Tauschen function brings in number theory, cryptography, and density limits. And what unites all of these is each concept quantifies the probability of structure of independence. No fixed points, full surjections, or coprime residues. In different contexts, these mathematical objects count how often a structure is maximally independent, and in doing so, they link discrete mathematics, number theory, and analysis. That's all. Thank you for your attention. I'd be happy to take any questions.
Супер. Дякую вам дуже. Було цікаво послухати та побачити такі дійсно гарні тотожності та закономірності. Давайте перейдемо до питань. Чи є в когось? Прошу, задавайте.
Так, в мене є. Хотіла запитати, чи можна буде якось також отримати посилання на це або цей файл, щоб ще хочеться перечитати та подивитися, дуже цікаво.
Так, звісно, ми можемо це обсудити особисто в повідомленнях тут в Zoom, або це буде в збірці конференції, якщо ні.
Добре, дуже дякую.
Так, будь ласка.
Давайте почекаємо, може ще в когось назріє питання.